This call is now being recorded.
Yeah. Good evening, students. Today, Prerana get lecture 3 on transformer. So here, see here in transformers, types of transformer, basic construction from there are three types of transformer we are classified: basis of construction and basis of winding and basis of coolant. Generally, we are going to be used in a case of basis of construction, that is core type of transformer and cell type transformer and spiral core transformer. So same transformer we can call as a name. In case of windings, those transformer also we can call step up transformer, step down transformer, and isolation transformer. So based on coolant, same transformers we can call as a name: oil filled self cooling transformer, oil filled water cooling transformer, air blast transformer. So apart from this, we are going to be mainly studied for in gate point of view core type transformer and cell type transformer. Either maybe core type transformer is step up transformer or otherwise step down transformer. And also cell type transformer, either maybe cell type transformer is step up transformer, either maybe step down transformer. So generally in both types of transformer, there is LV windings and HV winding. There is LV winding and HV winding. Here LV winding means low voltage winding, HV winding means high voltage winding. So when we are going to be given as an A input for LV winding, that winding we can call as an A primary winding. So then automatically we are going to be connected HV winding to the load. So means here the transformer act as a low voltage to high voltage. That is nothing but step up transformer. While same transformer we are going to be used when input is given to the HV side, high voltage side, then load is connected to LV side. Then the same transformer we can act as a step down transformer. So means either core transformer, maybe step up transformer, maybe step down transformer. Similarly, cell type transformer also step up transformer and step down transformer. See here, basic, there is a types of transformer, core type transformer and cell type transformer. So here, see here, it is a core type transformer. Here three cores, two cores and here three cores for three phase winding. It is in a single phase winding. It is in a three phase winding. Similarly here, see here, single phase winding for cell type transformer and three cell type transformer for three phase windings. So these are the basic types of transformer: core type transformer and cell type transformer for single phase and as well as three phase. So see here, there are main differences for core type transformer and cell type transformer. So here this is a core. Core is surrounded by the winding. This is the winding. Core is surrounded by the winding. In a case of shell type transformer, so it is in a core. Core is surrounded by the winding. Here winding is surrounded by the core. In core type transformer, core is surrounded by the winding. In shell type transformer, winding is surrounded by the core. So for that here there is a differences between core type and cell type. In core is surrounded by the winding. In shell type, winding is surrounded by the core. And also in there are main differences between cell type and core type. In this also, in core type transformer, the leakage flux produced is less when compared to core type transformer. Here there are some basic differences. That was nothing but regarding leakage flux. In leakage flux, core type is more, and leakage flux Shell type is less. So here mechanical strength is less. Why? Because the winding is surrounded by the core. But here mechanical strength is high. Shell type transformer. Why here mechanical strength is high in the sense the winding is surrounded by the core. So for that reason here shell type transformer is having more mechanical strength. And also here insulation requirement is less in a case of core type transformer. Insulation requirement. Why? Because in core type transformer, so first we are going to be cut into LV winding, HV winding into two equal halves. Nearer to the core, we are going to place it as in a half LV winding, and after then on LV winding, remaining half type of HV winding we are going to be placed. But in a case of shell type transformer, so alternatively we are going to place as in LV winding and HV winding. So for that here in core type transformer nearer to the core we are going to place it as an LV winding. But in a case of shell type transformer nearer to the core we are going to place either maybe LV and as well as HV. For that amount of insulation is required in a case of shell type transformer. In shell type transformer. So in a case of core type transformer regarding copper winding, the amount of copper required is more in a case of core type transformer. The amount of copper required is less in a case of shell type transformer. Why? Because first of all, first we are going to place nearer to the core is half LV winding. On that LV winding, half HV winding is placed. So for that, it requires more copper winding in case of core type transformer. While coming into shell type transformer, so we are going to be alternatively we are going to be placed. That is nothing but in sandwich manner. So for that, first nearer to the core we are going to place it as an LV winding, and nearer to the core we are going to place it as an HV winding. For that amount of copper required is less. So these are the major differences between the core type transformer and shell type transformer in regarding gate point of view. See here, transformer, there is a step up transformer and step down transformer. Means, so see here, primary coil and secondary coil. So what basis we can say that one is primary, another one is secondary, and means primary means which is connected to the source, that winding we can call as a primary coil or primary winding. The winding which is connected to the load, that winding we can call as a secondary winding. So means see here, so 110 by 120 volts. So means 110 volts is a primary and 120 volts is the secondary. So for that it act as a step up transformer. So see here second diagram, in this diagram 220 by 240. 220 by 240 here. So sorry, here 110 by 120 volts, here 220 by 240. We are going to be changes. We are going to be changes means here we are going to be taken as a high voltage winding, that is 220 by 240. Here secondary is 110 by 120. So for that reason here high voltage, here it is in a low voltage step down transformer. Here it is in a low voltage, here it is in a high voltage step up transformer. So isolation transformer. What is meant by the isolation transformer? That is nothing but the primary voltage, that is nothing but LV voltage and HV voltage. Both voltages are equal. The number of turns we provided primary winding and secondary winding both are equal. Such a type of transformer we can call as an isolation transformer. It is an isolation transformer. So generally where we are going to use it as a step up transformer means in generating station. In generating station generally we are going to use step up transformer. Where we can use a step down transformer in distributed networks and your home applications also. We are going to use it as a step down transformer. But coming to isolation transformer, where we are going to use it as an isolation transformer means, so here these transformers are required for protection purpose. So means we are going to be isolated any fault occur in the primary with effect of without effect of secondary, in the sense for the areas we are going to use it as an isolation transformer. This transformer generally we are going to be used as in a measure the voltages and currents in a case of substations. For that we are going to use it as an isolation transformers. the basic equation of transformer. The basic equation of transformer is ERMS is 4.44 B max A supply frequency into number of turns in the primary. So it is in a secondary equation E2, secondary equation. So here E1 by N1 is nothing but induced EMF per turn in the primary. E2 by N2 is nothing but EMF induced in the secondary per turn. The EMF per turn in the secondary. The EMF induced per turn in the secondary is nothing but E2 by N2. In primary is E1 by N1. From that we are going to obtain so 4.44 pi mf. Means from this we are going to say that the induced EMF per turn in the primary and secondary is same, but number of turns we are going to be placed in the primary and secondary, we can say that low voltage winding and high voltage winding. So see here, transformer is operated on under no load condition. That is ideal transformer. So means already we know that when transformer is operated on no load condition means there is some iron losses. Suppose it is an ideal transformer means it is an ideal transformer. The iron losses are zero. When iron losses are zero means see the vector diagram how it look like. So V1 is the supply voltage. When V1 is the supply voltage given to the primary winding, when IMU current starts flowing through the primary winding, this is the IMU current. Because of that IMU current, there will be a flux phi m is created, main field flux. So this flux is linked with the primary and as well as secondary. Automatically an EMF will be induced E1 and E2 according to Faraday's laws of electromagnetic theory. So see here, the primary winding is in a pure inductive coil and also secondary winding is in a pure inductive coil. Then automatically V1 is applied. The I is lags V1 by 90 degree. V1 by 90 degree. So automatically from the EMF equation, the flux also lagging induced EMF E1 by 90 degree. That is nothing but E1 lag pi m by 90. Similarly, E2 also lag pi m by 90 degrees. So this is the basic vector diagram for as an ideal transformer under no load condition. So see here we are going to take some assumptions for ideal transformer. Practically it is not possible while considering to some in ideal cases we are going to take some assumption. What are those assumptions? It requires infinite amount of permeability. It requires infinite amount of permeability. So whatever may be the flux produced in the primary winding, that flux is going to be linked with the secondary winding through the core of the transformer. When we are going to be design the transformer core is infinite amount of permeability. Whatever may be the flux produced in the primary winding, same flux is going to be total amount of flux is going to be flows through the transformer core and it will link it with as a secondary winding because of when we are going to be provided infinite permeability. So second assumption is core losses is zero. The winding resistance is zero. Leakage flux also zero. BH curve is linear. So these are the main assumptions for as an ideal transformer. So here first point is it requires infinite amount of permeability in the sense when it requires IMU current, the excitation current required for this infinite permeability of the transformer is zero, nearly and approximately zero. So the excitation current required is very very small when we are going to be design the transformer with high permeability. Then here core losses are zero. We are going to be assuming that there is no winding resistance. Why? Because it is an ideal transformer and leakage flux also zero. The BH curve is also linear. Now see the transformer under no load condition, practical transformer. See here, it is in a practical transformer, phasor diagram. It is an equivalent diagram. Phasor diagram. See here, before in this phasor diagram, No load angle pi naught is exactly 90 degrees. Exactly 90 degrees. Why? Because there is no core loss component. There is no core loss component. When we given V1 voltage to the primary winding, there is a IMU current starts flowing through the primary winding. Because of this primary current, there will be primary flux will be set up. Main field flux will be set up. So here, for that reason, here IMU, that is excitation current, lag V by 90 degree. 90 degree. While coming into in this, so V1, here V1 is an applied voltage. So when V1 voltage is given to the practical transformer operated under no load condition, no load condition, there is a IMU current starts flowing through the primary winding. Because of this IMU current, there will be primary flux will be created. This flux is nothing but useful flux or required flux. This flux is chosen a low reluctance path, that is nothing but transformer core, which linked with primary and as well as secondary, and EMF will be integers E1 and E2. So see here, there will be additional amount of current is drawn from the supply mains to overcome the no load losses. Those losses are nothing but core losses. Here this IW component is nothing but core losses component. Actually, what are the core losses or existence? Core losses are two types of core losses: eddy current losses and hysteresis losses. Eddy current losses and hysteresis losses. See here, for example, when flux is flows through the core of the transformer, this flux is also linked with windings, primary winding and secondary winding, and EMF will be induced. That induced EMF is E1 and E2, our required induced EMF. In addition to this, this flux is going to be linked with as in a core of the transformer, and EMF will be induced. So your core is having closed path. For that, there will be eddy currents are developed in the transformer core. So for that, some amount of current is drawn from the supply mains. And also the flux flowing to the transformer core will be alternating flux. Because of this, due to alternating flux, due to reversal of flux passing through the transformer core, there will be some loss takes place in the transformer core. Those losses we can call as a hysteresis losses. So for that also some amount of current is drawn from the supply mains. This total current drawn from the supply mains to overcome the iron losses, we can take as an IW component. IW component. See here, what is that component? IW component. This is the component. What is this current? Actually, we can take it as an IMU current. The purpose of IMU current is to maintain that, to sustain the flux in the transformer core. What is the IW component? To overcome the no load losses, that is nothing but core losses or fixed losses. Why? Because flux in the transformer core is constant from no load to full load. This flux is constant, automatically this iron loss also constant. So means when V1 is given to the transformer, practical transformer, there is a I naught current is drawn from the supply mains. There is a I naught current is drawn from the supply mains. That I naught current is resolved into two components. One is IMU component, another one is IW component. What is the purpose of IMU component? In the sense to sustain the flux in the transformer core. Because of that flux, our required EMFs are produced, that E1 voltage and E2 voltage. So one more component, what is that component? IW component. Because of this IW component, to overcome the core losses, it is a loss component. This IW component is in phase with V1. Why? Because it is a loss component. So this is the transformer and or no load condition, operated on no load condition. So it is in a no load current I naught. I naught is equal to I mu plus IW. I mu plus IW. So it is in a phasor diagram equivalent circuit under no load condition. No load condition means automatically. So here the amount of current is drawn from the supply means I not current. Because of that, the winding resistance also small in the primary winding. Then we can neglect the uh, primary copper losses. Then what is the amount of power is drawn from the supply means under no load condition? Only. So from this phasor diagram, see the IW component, RQ component of current. That IW is equal to I naught into cos pi naught. I mu is equal to react component of current, I naught into sin pi naught. I naught into sin pi naught. From that we are going to be evaluated this R naught parameter. R naught parameter is V1 by IW. Similarly, X naught parameter. That X naught parameter is V1 by I mu. Transformer under loaded condition. So when we close the switch, that is nothing but transformer under loaded condition. When transformer is loaded, there is a secondary induced voltage drive current through the load. Because of this secondary current, there will be phi 2 flux is created. Phi 2 flux is created. This phi 2 flux opposes to the main field flux. Then E1 and E2 voltages are reduces. So when E1 and V2 voltages are reduces, there will be a potential difference exist between the V and E1. Because of this potential difference, V1 pumps extra current. That current is nothing but I1 dash current. That is nothing but load component of primary current. So how much current is that because of the load component of primary current, there will be a creation of load component of primary flux, which is equal and opposite to phi 2 flux. Then net flux in the transformer is constant. Then automatically we are going to say that what is the current is drawn from the supply means under loaded condition is I1 current. This I1 current is resolved into two components. One is I naught plus I1 dash. What is the I naught? That is nothing but no load current. What is the I1 dash? That is nothing but load component of primary current. Vector sum of I naught plus I1 dash. So this I1 dash is also we can write down K into I2 according to this primary and secondary terms. See the phasor diagram. How is the phasor diagram of transformer under loaded condition? So when V1 voltage is applied, there is a I naught current is flows. That I naught current is resolved into two components. One is I mu and IW. IW. And when load is connected, if it is an unit resisting load means automatically there is I2 current starts flowing through the secondary winding. That I2 current is in phase with V2. Then automatically there is a load current I2 dash current is drawn from the supply mains. So I2 is anticipated with I2 dash. The net current is drawn from the supply main is a vector sum of I0 plus I2 dash. That is nothing but I1 current. If it is an inductive load. So inductive load means automatically I2 lag V2 by some angle pi 2. It's a pi 2. Here in phase both are. What about the pi 2 here? 0. Here pi 2. So here I2 lag E2 by pi 2. So I2 is anticipated with I2 dash. Then what is the supply current drawn from the supply means I1 is vector sum of I0 plus I2 dash. So see here equivalent circuit of transformer. So V1 and R1 X1 are series branch parameters and R0 X0 is shunt branch parameters. Then E1 is the induced voltage in the primary and E2 is the induced voltage in the secondary. When load is connected, there is a winding resistance, there is a leakage flux developed in the secondary winding. For that we can represent R2 and X2. Next, losses in transformer. What are the losses in transformer? Major losses, core losses and copper losses. In core losses, hysteresis losses and eddy current losses. Already we have discussed these losses. And copper losses. What is meant by the copper losses? The winding is having primary winding is having R1 resistance and secondary winding is having R2 resistance. For that, there will be primary copper losses and secondary copper losses developed on the transformer. See here. It is in a primary copper losses. These are secondary copper losses. The total copper losses represented with respect to primary side I1 square into R01. The total copper losses represented with respect to secondary side I2 square into R02. So copper losses at x fraction of load, we are going to be taking x square into copper losses. So generally these losses we can call as a variable losses, the copper losses. Why? Because these losses are depends on load current. When load increases, load current increases. Based on this load changes, this copper loss also changes. For that reason, we can say that these losses are nothing but variable losses. So where we can see the maximum efficiency means the maximum efficiency occurs at copper losses is equal to iron losses. See here, generally we are going to be represented the rating of the transformer in kVA. So why? Because there are major two types of losses occurs in transformer. What are those losses? Iron losses and copper losses. The iron losses are depends on supply voltage. Why? Because when V1 voltage is given to the transformer, so means see here V1 voltage is given. This V1 is directly proportional to flux, and iron losses are flux losses. Similarly, copper loss are depends on load current. That's why generally we can represent a transformer rating in kVA, volt ampere. So means iron loss are depends on voltage and copper loss are depends on current. Under no load, there is no copper losses. When load increases, the copper losses are increases. So generally the ratings of the any electrical device we are going to be represented based on heat developed on that mission. Heat is nothing but as a losses in electrical machines. So here, what are the losses? Major losses, iron losses that depends on voltage, and copper losses. Those losses are depends on current. So that's why we are going to represent a transformer in generally kVA rather than kW. Efficiency of the transformer. So we know the output power of the transformer. That is nothing but efficiency of the transformer is output power in kilowatt hour by output power in kilowatt hour plus core losses plus copper losses. Generally output power by input power. This input power we can call as an output power plus losses. So from this we can take it as a formula Vi cos phi by Vi cos phi plus core losses plus copper losses. So where we can obtain the equation when iron losses is equal to copper losses, we can get the maximum efficiency. See here, it is an efficiency curve. So in this point of view, you can obtain iron loss is equal to copper losses. Voltage regulation. So what is meant by the voltage regulation means it is a change in terminal voltage to rated terminal voltage. It is change in terminal voltage to rated terminal voltage. When this will be happen in the sense under loaded condition. There is no load in the sense the no load voltage V2 is equal to E2. When load is placed automatically, the secondary voltage drive current through the load, automatically there will be I2 R2 drop and also I2 X2 drops takes place on the secondary winding. Then automatically the load voltage is reduces because of this voltage drops existence. So that's why there will be a change in terminal voltage to rated terminal voltage when the transformer is operated under no load to full load condition. So for that we are going to obtain the equation, voltage regulation equation I2 R naught to cos pi 2 plus or minus I2 X naught to sin pi 2 basic equation by V2, plus for lagging minus for leading. So when we are going to be taken as a condition for maximum voltage regulation, so where we can get the maximum voltage regulation means at lagging power factor we are going to be obtain the condition for maximum voltage regulation, that is tan pi is equal to percentage of x by percentage of r. Condition for minimum voltage regulation where we can obtain the zero voltage regulation is that is nothing but percentage of x by percentage of z. Transformer there is open circuit test and short circuit test of transformer. So what is the main use of this open circuit test of a transformer? To obtain the to find out the core loss of transformer we are going to be conduct open circuit. In this open circuit, see here a transformer, generally this open circuit test is conducted on low voltage side rather than high voltage side. Why? Because here we are going to be measure the core losses. When we apply the V1 voltage, rated voltage, when we conduct on a low voltage side, less voltage voltmeter is required to measure the low voltage. So while we are going to be conduct high voltage side, the voltmeter range required is high means, and also we are going to be applied a high voltage. Because of that high voltage, there will be rated flux is set up in the transformer core. So for that reason, generally in open circuit test, we are going to be conducting LV side rather than HV side. What is the main reason behind this? So the meters ranges required for LV side is less when compared to HV side. So means here we are going to be given V1 voltage, then by adjusting the auto transformer, apply rated voltage to the primary winding. Here we are going to be connected as a wattmeter, ammeter and voltmeter on primary side. This wattmeter will give us as a core losses and ammeter will give as a no load current and voltmeter will give as a rated voltage of the transformer. So here secondary side is open circuited means the I2 current is zero, there is no copper losses in the secondary. Because of closed path exists in the primary winding, there will be a small amount of copper losses will be existence. These losses are we are going to be neglect. Why? Because transformer is operated under no load condition means it will draw minimum current from the supply means less current. So because of this less current, the winding resistance also very small. Then this loss also very small. Then we can neglect these losses. So by conducting this open circuit test, whatever may the power drawn from the supply means under no load condition, that will be read by wattmeter, that will be given as an a only core losses of the transformer. So this is the equation W naught equal to V naught I naught cos pi naught, that equal to core losses. So means here if you want to find out the cos pi naught no load angle, cos pi naught W naught by V1 into I naught. V1 into I naught. Pi naught is equal to cos inverse of that value. So generally this pi naught value asked in gate point of view examinations. Then we are going to be calculate IW component. How to calculate IW component? That component is nothing but I naught into cos pi naught. I mu, I naught into sin pi naught. Already we know these values. So what is the main reason to conduct this test? To find out the shunt branch parameters and no load angle of the power factor and no load power factor angle of the transformer and core losses. Short circuit test. Short circuit test. Generally, this short circuit test is conducted on HV side, high voltage side, and low voltage side we are going to be short circuited. Why? Because in high voltage side the ammeter range required is very less when compared to low voltage side. So see here in this test we are going to be applied reduced voltage, still rated currents are flows through the primary as well as secondary windings of the transformer. So what is the main use of this short circuit test? To obtain the copper losses. To obtain the copper losses. And also series branch parameters. Those are nothing but R01 and X01 with respect to primary side. Suppose if you want to calculate on secondary side R02 and X02. So what is the main reason to conduct this test is to find out the copper losses, full load copper losses, and series branch parameters. So see here, this is the circuit diagram. In the circuit diagram, LV is short circuited and HV we are going to be conduct a test on HV side. So here we are connected voltmeter to measure the reduced voltage, ammeter to measure the rated current flows to the windings, and wattmeter to measure full load copper losses. See here, when we apply the reduced voltage by using auto transformer, by observing the ammeter, when the ammeter reads as in a rated current, then we stop the applied voltage. So means for this, in this case, the high voltage winding is here we are going to be applied reduced voltage, still rated currents are flows through the primary as well as secondary windings of the transformer. When this ammeter reads as in a rated current, then this wattmeter will give as in a full load copper losses, then ammeter will give as in a full load current. So what about the iron losses in this test? In the sense, in this test we are going to be neglected the iron losses. Why? Because here we are going to be apply the reduced voltage, reduced voltage. Then automatically flux flows in the transformer core is very small value. For that, the core losses developed also very small. So for that reason, we can neglect the core losses developed in this test. Then total losses measured by wattmeter will give us as a full load copper losses. So here, what are the parameters? Here we are going to obtain shunt branch parameter R naught and X naught. This is the X naught value. Sampana test and back to back test. Sampana test and back to back test. So what is the use of this test? Also, this test in this test, there is a small difference between this SC, OC and SC test. Here we are going to be separately measured. We conduct as an open circuit test. Then we are going to be removing the connection. Next we are going to be conducted. It will take some time. Then we are going to be conduct SC test. But in case of Sampana test, back to back test, simultaneously we are going to be measured iron losses and as well as copper losses in this test. That's why this test also we can call as a heat run test, and also it will give us an accurate results when compared to OC and SC test. See here some problems in gate point of view. A single phase 50 Hz transformer has 80 turns on the primary winding and 280 turns on secondary winding. The voltage across primary is 240 volts. 1. Calculate maximum flux density in the core, EMF induced in the secondary. Consider cross-sectional area of the core is 200 centimeters square. So already we know that basic formulas. E1 RMS is equal to 4.44 BMA FN1. From that input voltage is 240 volts, 4.44 A already given. So 80 frequency. Then we are going to be obtain B 0.675 Weber per meter square. And also they are asked what is the EMF induced in the secondary. Already we know that E2 by E1 is equal to N2 by N1. The induced EMF pattern in the primary and secondary is same. For that reason, E1 by N1 is equal to E2 by N2. From that, we are going to be obtain this relation. Then easily we are going to be obtain E2 voltage. Next, second problem. 11,000 by 400 volts distribution transformer takes no load primary current is 1 ampere at zero point 0.2 power factor lagging. Find core losses current and magnetizing current and iron losses. From the phasor diagram, already we know that IW is equal to I naught cos pi naught. Then already here power factor is 0.24. 0.24. I naught is 1 ampere. 1 into 0.24. So 0.24 ampere. Then I mu. I naught into sin pi naught. I naught is 1 ampere. And it will be a cos pi is equal to 0.24. Pi is cos inverse of 0.24. Then that will be substituted in sin pi. We can obtain Sine P is 0.97 ampere. Then what is the already we know that W naught is equal to V naught I naught cos pi naught. That is 960 watts, 96 watts. Yes, already this is an input voltage V1. Next, see here one more problem. A no load ratio of 58 single phase transformer is 6000 volts by 250 volts. Estimate the number of turns in each winding if maximum flux is 30 milliweber in the core. 30 milliweber in the core. So already we know that pi is equal to B max into A. So already we know that what is the B max? B max is equal to see here. So B max is equal to pi by A. From that pi is equal to flux density per unit area. Flux per unit area is nothing but flux density. So when we substituted this one, 600 volts, 4.44 into 30 milliweber into N1 into 50. V1 is given, V1, this is 6000 volts, V1. And then a flux, this one is flux and 50 hertz frequency. Substituted, we can obtain N1 is 900 tons. Similarly, N2 we can obtain 38 tons, a basic problem. Next, find the following parameters: active component and reactive component of load currents. Second, no load current of 230 volts by 115 volts transformer. The input, the if the power input on no load to the high voltage is 70 kilowatts and power factor on no load is 0.25 lagging. Find the following parameters. What are those parameters? Active component and reactive component. That is nothing but IW and I mu. And no load current I naught. The input on no load to the high voltage winding is 70 kilowatt. Here 230 by 115. High voltage means 230 input side. So from that simply V naught I naught cos pi naught. So from this, what is the we want actually I naught. Here they are not given as an I naught current. So V naught is 230, cos pi naught is 0.25, and P is 70. Means 70 is equal to 230 into I naught. We don't know. Same as it is we write. Next cos pi naught 0.24. Then I naught is equal to, you can obtain this value. So IW is equal to I naught into cos pi naught 0.34 amperes. I mu is equal to I naught into sin pi naught 1.178 amperes. So it is an active component of current, it is an reactive component of, it is an no load current. Here there is active component, reactive component and no load. Yes. So these are the basic things in transformer we studied for gate point of view in today's class. Yes. And also one more last problem is there, that is problem on efficiency. The efficiency of 1000 kVA 110 by 220 volts 50 hertz single phase transformer is 98.5% at off full load 0.8 power factor lagging, and 98.8% at full load unity power factor. Determine the iron losses, full load copper losses, maximum efficiency at unity power factor. Very, very important problem here. So the efficiency of 1000 kVA 110 by 220 volts 50 hertz single phase transformer is 98.5% at half full load, 0.8 power factor lagging, and 98.8% at full load unity power factor. So from this we are going to write down already what is the formula for the efficiency. V2 I2 cos pi 2 by V2 I2 cos pi 2 plus core losses plus copper losses. So from this, so first 98.5% by 98.5 by 100 efficiency. So offload means 1 by 2, 1 by 2. So rating 1000 kVA means 10,000 into 10 to the power of 3. What is the power factor? Unity 0.3, 0.8 power factor. First case. Second case, 98.8% full load condition. But power factor is unity here. It is a unity 1. It is a 0.8. These are the two different cases. One is off load 0.8 power factor. Second one is full load unity power factor. Your percentage efficiency is 98.5 at off load, 98.8 at full load. So from this equation, two equations we are going to be resolving, we can obtain core losses and copper losses. Core losses and copper losses. So from that first one, determine the iron loss. Already from this, when we solve these two equations, we are going to obtain. This is the first one answer. Next, it is in a full load copper losses. Full load copper losses. Next question, what is the full load copper losses? PCU. PCU is in a full load copper losses. Whatever may the, when these two equations are solved, we can obtain full load copper losses and core losses. PCU is in a full load copper losses. P core is in a iron losses. Maximum efficiency at unity power factor. Maximum efficiency at unity power factor, actually. So maximum efficiency at unity power factor means that is nothing but where we can obtain the maximum efficiency, square root of core losses by copper losses. That value is 0.71. Then will be substituted at this load. So means efficiency eta is equal to 0.71 into rating of the transformer, 10,000 into 10 to the power of 3 unity power factor. Here they ask unity power factor, for that reason taken 1. So again output power plus 2 into core losses 2 times. Why? Because we can obtain the maximum efficiency at iron losses equal to copper losses. So for that we are going to obtain the efficiency at 98.87%. So this is also very, very important problem for the gate point of view. Yes. Yeah, thank you all of you, those who are those who are participated actively in this session. Thank you. Next session tomorrow we will see in synchronous missions and induction missions. Last session, lecture 4. Thank you all of you.